here is a nice application of all the techniques that we've learned so far, which will be incredibly useful if you ever take partial differential equations. So the problem is as follows. Let's find all the values of lambda for which this differential equation y double prime equals lambda y with 0 at 0 and 0 at pi has a non-zero solution. So the key is non-zero. And we will see there will just be selected values of lambda for which this works. And the way to visualize this is simply we have the interval 0, pi, and we require our solution to be 0 at 0 and 0 at pi. So y of pi equals 0, and we kind of want to figure out the value y of t. Now, this is important to understand. Before what we had initial conditions where we specified the function and its derivatives. So before we had initial conditions, where we specified, I don't know, y of 0 equals 3 and y prime of 0 equals -4. But here what we have is what's called a boundary condition. Boundary condition, where we specify the values of your function at the endpoints of your interval. So y of 0 equals 0, and this time not the derivative, but the value at a different point equals 0. That's one thing. And the second thing I want to talk about, so this is very important in applications, because sort of in a simplified fashion, here, y of t represents the temperature of a metal rod. Sure. Of metal rod. But kind of not at time t, but at position t. And this y of 0 equals 0 and y of pi equals 0, this just means that we're putting an ice cube on both sides of the rod. This is called insulation. So y of 0 equals 0 and y of pi equals 0 means you're insulating both sides of the rod. Both sides of the rod. And kangaroo. But really, the true reason this is important is if you ever take partial differential equations, because this will be a very important step to solve what's called the heat equation and the wave equation as well. But for now, let's now solve this problem. So we want to find the values of lambda for which this has a non-zero solution. So as usual, let's find the auxiliary equation. So again, our differential equation is y double prime equals lambda y. So the auxiliary equation is r squared equals lambda. And notice the behavior of the solution really depends on the sign of lambda. Because, for instance, if lambda is 0, we have a repeated root. When it's positive, we have distinct roots. When it's negative, we have complex roots. And that's why it's natural to really split this into cases, where case 1 would be lambda positive, case 2, lambda 0, case 3, lambda negative. Now, what I want to show you now will be very complicated, but I do want to tell you that it'll always be the same technique. So it looks difficult the first time, but the more you do it, the more you'll see it's always the same. Now, suppose lambda is positive. In order to get rid of nasty square roots, notice that any positive number is the square of another positive number. So notice that if lambda positive, then lambda is the square of some other positive number. So for some omega positive. So for instance, if lambda is 9, then 9 is 3 squared. So omega would be 3. Now, of course, 9 is also minus 3 squared, but we can always choose a positive case in this case. So, and by the way, this omega has a nice physical application. Omega is sometimes called the frequency of your system. See, of system. Okay, so in this case, what we have, our auxiliary equation is r squared equals lambda, which is really omega squared. And therefore, taking square roots, we get r is plus or minus omega. So think plus or minus 3, which then gives us the general solution. Y is a e to the omega t plus b e to the minus omega t. So if you, let's say, get plus minus 3, it's a e to the 3t plus b e to the minus t. And now what we want to do, we want to plug in our boundary conditions. So let's plug in y of 0. So y of 0, it's a e to the 0 plus b e to the 0. That is a plus b. But remember, y of 0 is 0. So a plus b is 0. So b is minus a. So already we can see y of t is a e to the omega t minus a e to the omega, e to the minus omega t. Now we want to use our second boundary condition, y of pi equals 0. So what we get is a e to the omega pi minus a e to the minus omega pi equals 0. And therefore, a e to the omega pi equals a e to the minus omega pi. Now, ideally, what we want to do, we want to cancel out the a. But in order to do that, we just need to make sure that a is non-zero, because we can't divide by 0. However, here it is. So a is non-zero, because if a were 0, then we can go back to y of t. It would be 0 e to the omega t minus 0 e to the minus omega t, and we would get 0. But remember, the goal is to find non-zero solutions of this. So we can assume that a is non-zero because we want non-zero solutions. And this then gives us e to the omega pi equals e to the minus omega pi. You can take logs and then get omega pi equals minus omega pi. You can cancel out the pi here. And essentially, what you get is 2 omega is 0, and therefore omega is 0. But the problem is, if omega is 0, then lambda would be 0. Lambda, remember, is omega squared, is 0. And again, this contradicts the fact, so the double arrow is contradiction, that lambda is positive. So in this case, what we can really conclude is that there are no non-zero solutions. Because if we assume there's a non-zero solution, we find this contradiction. this case, no non-zero solution. Which is okay, that can happen. It do be like that sometimes. So let's continue and do the case lambda equals 0. In this case, the auxiliary equation is r squared equals 0, which gives r equals 0, but repeated twice. And then that gives you y of t equals a e to the 0t plus b e to the, no, because you have a repeated root, it's a e to the 0t plus bt e to the 0t, which is simply a plus bt. And then once again, you plug in y of 0 equals 0. That tells you a plus b 0 equals 0, and therefore a equals 0. So in this case, y is 0 plus bt, so just bt, kind of like BTS, but cooler. And then we have y of pi equals 0. That tells you b pi equals 0. You can divide by pi, and then you get b equals 0. But that is a problem because, well, y of t then becomes 0t, which is 0. And again, which is a contradiction because once again, we want non-zero solutions. So our conclusion here is that also in this case, we have no non-zero solutions. No non-zero solutions. Solution. And that's where we can start sweating, because we saw in case 1, there were no non-zero solutions. In case 2, there were no non-zero solutions. Well, let's see what happens in case 3. Hopefully they'll work. I mean, it will work, because why would I teach about it, right? So let's assume lambda is negative. And just like in case 1, we can assume lambda to have a special form. So in this case, lambda would be minus omega squared, where omega is some positive number. And again, just as a quick example, if lambda were minus 9, that would be minus 3 squared. So in this case, omega would be 3. Again, you could use minus 3, but it would give you the same answer. That's why it's okay to assume omega is positive. All right, and in this case, so what's the auxiliary equation? R squared equals lambda. In this case, it's minus omega squared, which by taking square root, r would be plus minus omega I. Think plus or minus 2i. And in that case, you would get cosines and sines. So a cosine of omega t plus b sine of omega t. Okay, and just like before, let's plug in the boundary conditions. So y0, it's a cosine of omega 0 plus b sine of omega 0. But that just simplifies. Cosine of 0 is 1, sine of 0 is 0. So this gives you a. But remember, y of 0 is 0. So this gives you a equals 0. And therefore, y of t is b sine of omega t. And let's box this, because you will see in a second this will be extremely important. Not quite clear why, but in a moment. Okay, and now let's do y of pi equals 0. So y of pi equals 0, then b sine of omega pi equals 0. And once again, we want to divide by b. We just need to make sure it's non-zero. However, here it is. B is non-zero, because if b were 0, then y would be 0 sine of omega t, which would be 0, which again, we don't want. Okay. So what we get here now, sine of omega pi is 0. And at this point, you must be sweating a lot, because we saw that case 1 doesn't work, case 2 doesn't work, a is 0, we canceled out b. Oh no, but who is here to save the day? Peyam. Because remember, the zeros of sine are just multiples of pi. So omega pi is Peyam, where m is any integer, which gives you omega is m. It's kind of like the denouement here. So omega is m. But just one little thing. So we said m is any integer, but strictly speaking, it's any positive integer, since omega is positive. M needs to be any positive integer. So really, m is 1, 2, 3, And going back to our problem, which values of lambda work? Well, in that case, if omega is any positive integer, lambda, which is minus omega squared, becomes minus the square of any positive integer. So really, -1, -4, -9, etc. That is lambda. What about the solutions? Well, that's where box answer helps us. So for any omega we found, the corresponding solutions is just multiples of sine. So from the above, we simply have y is b sine of omega t, which in this case, since omega is m, b sine of mt. So what is the answer to the question? What is the epic conclusion? Well, couple of things. So the values of lambda that work is -1, -4, -9, etc. Those are what are called the eigenvalues. Like the previous video where the roots were the eigenvalues. So lambda is minus m squared, which is really -1, -4, -9, where m is 1, 2, 3. So please specify the values of m. And the corresponding solutions, or the corresponding y, is simply sine of mt. And those are called the eigenfunctions. So y of t equals sine of mt, which is really sine of t, sine of 2t, well, sine of 3t, etc. where again, m is 1, 2, 3. You may wonder what happened to the constant. Well, at this point, I invite you to watch the previous video again, because before we had something like a e to the 2t plus b e to the 3t, from which we extracted the basis functions, e to the 2t, e to the 3t. Here again, it's the same thing. So here, sine of mt are our basis functions. So we just care about the function itself, not about the linear combinations. And last but not least, why is this called an eigenvalue and eigenfunction? By the way, if you want a picture, you can look at the following. So sine of t looks like this. Sine of 2t goes like this twice. And then it just oscillates more and more, which is really cool. So maybe something like this. So I think sine of 3t, I think it oscillates 3 times. 1, 2. Maybe like this. So it just oscillates more and more. Last but not least, really here, so why is it called an eigenvalue and eigenfunction problem? This is in comparison with linear algebra, if you've taken that. So compare with linear algebra, the problem of finding eigenvalues and eigenvectors is really solving AV equals lambda V. Linear algebra. Here we have the same thing. If you notice, we have y double prime equals lambda y. So still some function of y equals a multiple of itself. And this in linear algebra is called an eigenvalue problem. Now, in the next video, we'll do this again, but you'll see really how similar it is to this example.